This will be a short video wherein we will discuss how to find the magnetic field intensity at the center of a current carrying circular loop. So to say, we have a circular loop which is carrying current, of course, and we want to find the magnetic field intensity at point O, that is at its center. We actually have looked into this the expression for magnetic field intensity at the center of a circular loop in the previous video, wherein we discussed how to calculate the magnetic field intensity at the axis of a current carrying circular loop. So we had a current carrying circular loop and we calculated the magnetic field intensity at this point. Then after, what we did is we brought this point P at the center O such that x was 0, and we saw that the magnetic field intensity at the center of the circular loop B comes out to be mu naught I by 2a. So in this video also, we are going to look at how to straight away jump to this expression. So sometimes you get a question to find the magnetic field intensity at the center of a circular loop, current carrying circular loop. So in which case, you will do what we are about to discuss in this video, rather than doing this elaborate derivation wherein first of all you will calculate magnetic field intensity at a point on the axis of the current carrying circular loop. Then after, you will consider x to be 0 such that your point P is at O. Okay, so rather than doing this whole elaborate derivation, you are going to do the following. So let us start. So what we've considered is, we've considered A to be the radius of the circular loop and I is the current flowing. So you can see current I flowing in the anti-clockwise sense. And we've considered a small elemental length dl over here. So due to current I flowing through this elemental length dl, the magnetic field intensity at point O is given by Biot and Savart's law. So according to Biot and Savart's law, the magnetic field intensity at point O due to current I flowing through the elemental length is given by dB, which is mu naught by 4 pi I dl sine theta by r squared. Now you can see from this picture itself that theta, which is the angle between the elemental length and the line joining the elemental length to point O, is 90 degrees. Okay, at any point you consider dl, the angle theta will always be 90 degrees. So r, that is the distance between the elemental length and point O, is the radius of the circle itself. So r is equal to a and theta is equal to 90 degrees. So therefore dB comes out to be mu naught by 4 pi I dl by a squared. So if magnetic field intensity at point O due to the elemental length is this much, then the magnetic field intensity at point O due to the whole circular loop will be a sum of the magnetic field intensity due to these kind of small dls. Okay, so therefore B, the magnetic field intensity at point O due to the whole circular loop, is given by B, which is integration of dB, so which is mu naught by 4 pi I upon a squared. All these are constants. I is a constant, a is a constant. Okay, so the only variable is dl. Okay, so integration of dl. Now when we add up these small dls, when we add up these small dls everywhere, okay, so what we are eventually getting? What we are getting is, we are getting the circumference of the circle. Now the circumference of the circle is given by 2 pi a, 2 pi into the radius of the circular loop. So B comes out to be mu naught by 4 pi I upon a squared into 2 pi a. So after simplifying, we get B is mu naught I by 2a. So therefore this happens to be the magnetic field intensity at the center of a current carrying circular loop.